Okay, so we're going to start AP Chemistry Unit 1. We have 14 of these to go through, so got a long road ahead of us. To shake off some of the summer cobwebs, I want to take a look at this problem. Right here, you have a really tall piece of glass, and it's a container. Does anyone know what that's called? Graduated cylinder. Very nice. So in our graduated cylinder, we have 4 different liquids, and the liquids are layered on top of each other. So just in general, what is making these liquids be on top of each other? Different densities. Correct. So comparatively, how would the densities be ranked in here? Heaviest on bottom, lightest on top. So what we're going to do is identify what liquid 3 is and what liquid 1 is based on the information given. So let's first start with the things that we know. We know that mercury has a density of what? 13.5. Well, I don't know what 13.5 is. 13.5 what? Grams per mil. If you ever have naked numbers in this class, you know something's wrong. You never write down a number unless we got a unit. All right, we know water has a density of 1.0 grams per mil. And again, this is at 25 degrees Celsius is what we're talking about here. What is 25 degrees Celsius about in our, okay, STP for some things other than gas laws, but I meant in terms of your life. If I ask you, if I say it's 25 degrees right now, would you feel uncomfortable? How would you feel? It's room temp, so this is pretty much what it is right now. It's a little, it varies a bit. Okay, so what are our options then? Let's start from the bottom here. I like to build up. What are our options for liquid 3 in our list? What could it be? Bromine? Could gold be it? Why couldn't gold be it? Exactly, it's heavier than mercury, so it would be under mercury. What's our other option? Dichloromethane. And our other option? Aluminum. Right off the bat, I can get rid of one of these options. Why can I get rid of dichloromethane? That's not the one I was thinking of, but if you want to get rid of it. Perfect. Dichloromethane is polar. What do you know about the things above and below water? Water's nonpolar? Water's polar, right? Since water's polar, what would happen between water and dichloromethane? They wouldn't react. What would they do? They dissolve in each other, so you wouldn't have a separate layer. Have you ever seen water poured with oil together? How you can shake it and it kind of mixes, but then it immediately separates? Okay, that's because of their polarities. What's on top and bottom then depends on their densities. All right, so it can't be dichloromethane for that reason, so I'm good with that. What about between aluminum and bromine? Nice. Aluminum is a solid at 25 degrees Celsius. So could that be it? No. So our answer is bromine. So because bromine then is nonpolar, it won't mix with water. Okay? All right. Let's look at liquid number 1. What are our options for liquid number 1? Hexane's a possibility, and ethyl alcohol is a possibility because that's between, that's lighter than the 1, which is what we need. And those are the only 2 lighter than 1. So which one is it? Hexane. Why? It's nonpolar and it won't mix with alcohol. Okay? So that's why, because I know you guys don't drink. You know nothing about alcohol. But when you buy alcohol at the adult liquor store, not that there's a kids liquor store, but at a liquor store, your alcohol is not pure. It's like 75 proof or 33 proof or whatever. That shows you that it is soluble in water. And these 2 layers would mix if we had the alcohol and the water next to each other. Okay? So Feel good about density a little bit, just getting some cobwebs out? Now we're getting into the math of chemistry, and we got to think back. Compare and contrast accuracy and precision. What's the difference? So accuracy is closeness to the true accepted value. Precision is repeatability, how close the answers are to each other. So if I were to step on a scale and it said I weighed 90 pounds, and I were to step on a scale again and it said I weighed 91 pounds, and again it said 90 pounds, and you're not going to hurt my feelings, is that scale accurate? No, nowhere near accurate. But what can you tell me about that scale? It's precise. Okay? So knowing that now, which set of measurements are precise? Which dartboard, or which, I should say, which player? The player is what's precise, the one throwing the darts. So it would be B and C. Good. Which set of measurements are accurate? Pretty much just C. And then which set of measurements are both precise and accurate? C. An interesting phenomenon which happens on occasion where we deal with taking an average to get an actual value. We'll have here, and this is our bullseye, you might have this going on. Is that very precise? No, not at all. But usually when you take an average of multiple trials, your average will be pretty darn close to the actual value. So to a degree, theoretically, you could have data that's not precise, but still be pretty accurate based on the average. Okay? All right, now let's explain the difference between exact number and an inexact number. This one caused first period a little bit of trouble. Inexact. I can't even spell. Oh, it's going to be one of those years. What do y'all think? Exact. Anyone have any ideas? Specific, okay. Irrational versus, that's kind of an idea. It's not exactly what we're looking for. Be defined by a variable. No. Let me give you a hint. What's different about these is the method in which the number is collected, or the number, where it comes from. So what do we do in science? We measure stuff. Would that be exact or inexact? No. Measuring stuff leads to inexact numbers. Why? Hey, if I were to use a balance in the back of the room that weighs out to 1 decimal place, that's going to be different than the balance I use that weighs out to 4 decimal places. Okay? So what would be another way to collect a number? It's really simple. You're probably going to go, oh, that was stupid. Counting. Nice. Counting. So if I were to say something weighed 1 gram, do you understand how that's different than me saying something weighed 1.0 grams or 1.00 grams? Okay? But if I were to say I've got 30 people in this room, does that mean anything different to you saying I have 30.0 people or 30.00 people? No. Okay? Counting numbers have an unlimited number of sig figs. So exact numbers are what we call counting numbers, and they have an unlimited number of sig figs because it doesn't make a difference in what that number means. Let's answer these. The number of faces, is that an exact or inexact number? Exact. Mass of 6 apples. Inexact. The number of seeds in an apple. Okay, got to be careful here. I'm just going to tell you right now, without giving you the answer, those two things have different answers. One's exact and one is inexact. I'm going to give you a second to look at it and see if anybody can figure that out. Can you figure it out? Grant. Right. But if I were to heat the liters up, wouldn't the quarts change too because it's a liquid in both? Okay. That's a good idea. That's not where we're going though. Jessica. Hold on just a sec. Very nice, gentlemen. I'm going to give you guys props, Pierce, Miles, and Christopher, for doing this. One of these conversions falls within the same system. When a system is developed, it's developed as a counting exact number. When you're going from one system to the other, one's trying to become like the other, so that is not an exact value. Okay, that's going to be a measured value. You have to make a measurement in order to make that connection. Okay, so if I'm going feet and miles, what is that? That's exact versus liters to quarts, inexact. Okay, so when we're doing stuff like this, where we're going from grams to kilograms and dimensional analysis and things like that, that is why we don't use the conversion factors in our significant digit determination at the end. We only use our given value. You never use your conversion factors when you're determining Sig Figs because those numbers are an unlimited number of Sig Figs. All right, let's talk about rules for counting Sig Figs. Review these. I know that y'all might have learned Pacific and Atlantic and all these tricks. You guys are big kids now, so we're moving on to just knowing the rules. Non-zero integers. If you have a number that's a number, I don't care what it is, it's significant. Now zeros cause some issues. There's something called leading zeros. If we have a leading zero like that versus that, these zeros are significant because in measurements, they mean something different in chemistry. A 0.01 gram is going to be very different than a 0.001 gram. Okay, and one instrument, which instrument's more accurate? The one that weighs to 0.01, the one that weighs to 0.001? This one, okay? So any leading zeros where a decimal place is present is going to be significant. All right, captive zeros. Captive zeros are considered significant. I call them sandwich zeros. If a zero is caught between two significant numbers, it itself is significant. All right, trailing zeros. You have two options. Those are trailing zeros, that's a comma, or, all right, trailing zeros without a decimal are not significant. A good example of this is if you were to go to Longhorn Stadium for a game and they announce there's 50,000 people here today. You'd probably be like, are there 50,000 people in the stadium, do you think? No, about 50,000, okay? What I could do to make this significant, I mean, it doesn't make sense because there isn't a 0.5 of a person, but if they were to say there's 50,000.5 people here, doesn't that in your head sound like they've actually counted and figured out exactly how many people are there? Okay, so anytime you start putting a decimal into it, the trailing zeros become significant. So I could have a balance. I have one in the back. It weighs out to 4 decimal places. And those are significant numbers. All right, we already talked about exact numbers. Any counting number having has an unlimited number of Sig Figs, so we don't really use them in our dimensional analysis or Sig Fig determination. And then here, we talk about scientific notation. Anything to the left of an X is going to be significant. So what is this number really? Is it 1? No, it's not 1. People, 100. It's 100, okay? So looking at this as is, how many Sig Figs does 100 have there? 1. Because we put it in this form, how many Sig Figs does it have? 3, okay? Can you tell me another way to make 100 have 3 Sig Figs instead of writing it in scientific notation? There's a couple things you can do. Decimal, okay? So you've made that number significant, and then this is a sandwich zero, so now you have 3 Sig Figs. What's another way? Bar. We can put a bar across the top. Again, you only have, some people put it on both zeros. You don't need to because of the whole sandwich zero thing. Putting it here makes this number significant because it's sandwiched. All right? So anytime you do scientific notation appropriately, where it's a number between 1 and 9, and then a point, everything to the left of the X is going to be significant. Bueno? See, I'm bilingual. I'm just kidding. All right, so easy. How many sig figs in A? 3. How many sig figs in B? I'm hearing dissension. 4 or 5. Which one is it? 5. Good. Why? Who said 4? Don't tell me who said it, but I'm figuring the person who said 4 was because of those. It's a trailing 0 with a decimal is important, okay? And then in an experiment, a span of time is determined to be 8.05 e negative 3. How many sig figs? 4. 1, 2, 3, 4. All right, I think you all got that. Okay, now we got to talk about sig figs when we're doing calculations. Our rules are different for multiplication and division compared to addition and subtraction. What we do most often is multiplication and division. And what you have to do in multiplication and division is round to the least number of sig figs. Round your final answer to the least number of sig figs. Okay? So what we have to do is look at what we're multiplying and figure out how many sig figs are in each, and then round to that number. How many sig figs in this 4.56? 3. How many sig figs in 1.4? 2. So I'm going to round my final answer to 2 sig figs. When you put this in your calculator, you get 6.38. We got to round that to 2 sig figs. Following normal rounding rules, 5 and above, you round up. We round to 2 sig figs, and we get 6.4. We do this with both multiplication and division. How does addition and subtraction differ? We don't round to sig figs, we round to decimal places. So we round to the least number of decimal places. So looking at this, how many decimal places are here? 2. How many decimal places here? 1, 3. So we're going to go ahead, what are we adding? Yeah, duh, yeah, we're adding. We're going to go ahead and add these up, and then our final answer, we're going to have to round to 1 decimal place. So we get 31.1. Okay? Let's practice this. So go ahead and get out your calculators. All right, so looking at our calculation here, this is a subtraction. So we're going to round to the least number of decimal places. So I'm going to put decimal places. How many decimal places are in this first thing? 3. How many decimal places are in this next number? 4. So we're going to round, not to sig figs, decimal places, right? So go ahead and shove that in your calculator and tell me total number you get without rounding out of it. 0.2738? Okay, so how many decimal places do I need to round this to? 3. So my actual answer is 0.274. Good. Let's look at the next one. It's an addition, so we round to least number of decimal places. Okay, I'm going to set you loose on this one. We have 3 decimal places here, 1 decimal place there. Someone holler out the correctly rounded answer for me. 105.6. Nice. Okay, moving on. We now are in the world of multiplication. So what are we going to round to here? The least number of sig figs. Here we have 3, and here we have 2. So what do you get when you just plug it in your calculator unrounded? All right, how do I round that to 2 sig figs? Because that is the least number over here. Okay, you're totally on your own now. Do that one. What'd you get? 0.067. Let's 0.0670 or 0.6? All right, let's check this. We had 3 here and 4 there. We have to round our final answer to 3. This leading 0 does not count, so we need those 3, so this is correct. Okay, this one is going to be fun. Now, in this particular problem, we're going to round after each operation because when you're really determining sig figs, technically, you're supposed to do that. However, on the AP exam, they'll actually accept, being a grader, I know because I've done this, will accept actual values when you round at the end. I'm okay with that when we get to actual real chemistry. But this particular problem I'm presenting you with is a problem asking you specifically about sig figs with no other chemistry associated with it. So we're going to do it the correct way here. So we're going to round after each step. So what is the first, based on order of operations, what do we do first? In the parentheses, right? So this is a subtraction. So that's a subtraction. We're going to round to least number of decimal places. So we're going to round to 3 decimal places there. And what is that number? 0.060? No, 3 decimal places, not sig figs. Got it? Okay. Now, what's the next thing we do? We do division. Now we're going to divide that by that. So, looking here, since we're dividing, we're finding least number of sig figs. How many sig figs in this top number? 2. How many sig figs in this bottom number? 5. So what are we going to round this division to? Okay, 2 sig figs, which would be what? Times 10 to the negative what? 4. Okay, so that's it. That's 2 sig figs. Now we're going to add it. Oh, my back. We're going to add it to 2.091. How many decimal places am I going to round to? 3. Someone didn't get caught. You know what most people try to say? They're thinking this is a decimal place and they're going to round to 1. Why is that wrong? There's a lot more decimal places than that because of that negative 4, right? So this is really 0.00061 plus 2.091, right? So the one with least decimal places is the 3. So we're going to round this to 3 decimal places, and I think you get 2.092, right? When you add, because that number is so tiny that you're adding to it. So I'm just telling you now, on the test, you will be asked just math problems, kind of like math class, doing things like this, okay? All right, let's look at some things that you need to know in regards to the different systems. I never expect you to know any of that by heart. In today's problems, there's a couple extra things that I want to write down to make the dimensional analysis go a little bit easier. Does anyone know how many feet are in a mile? 5380? 5280. 5,280 feet in 1 mile. That's going to help us a lot. What about runners, the kilometer to mile? 1,600 meters in a mile? That's a good one. 1,600 meters, which makes sense because it's 4 laps around the track, right? Okay, and that would be the correct amount. So that's going to help us with our dimensional analysis stuff. You do not need to know this by heart. What I do want you to know are your metric system units by heart. You have to know these. Don't memorize, memorize. The big ones you'll use pretty much every day is your centi, your milli, your kilo are the ones that are going to show up the most. But you know, nano and micro are important when we get to waves, and then mega is a good one to know as well. People get deci and deca confused. That's the reason that's up there. I just really want you to know that deci is small and deca is big. And a lot of really, the trick to this is realizing which one is big and which one is small. You know, kilo and milli are both 1,000, but which way does it go? Kilo is huge. So there's 1,000 meters in a kilometer. But are there 1,000 meters in a millimeter? No, it's reversed. There's 1,000 millimeters in meter. So just think through which ones are big and which ones are small. All right? So I want to practice some dimensional analysis. We're using a lot of the American system here. This is just strictly for the dimensional analysis practice. If I give you any American system on a test or quiz, I will give you the conversion. Okay? A pencil is 7 inches long. What's its length in centimeters? So I'm going to take my given. I need to use dimensional analysis to convert. I don't recall if they had it on here, but you probably know it. Yeah, it's there. Okay, so I need the conversion between inches and centimeters. What is it? 1 inch on the bottom, so that cancels, is 2.5 centimeters up top. Inches cancel, and what do you get? 17.787. We're going to stick with our given, okay? We're not going to use our conversion factor, so I want 3 Sig Figs, so it's 17.8. Do y'all get 8? I'm hearing some 9s. 8, okay. All good with that? Okay. The speed limit on the main highways is 55 miles per hour. If I were to put miles per hour into my dimensional analysis railroad tracks, what am I really saying? 55, what? Miles per, what is per? How do I put that in my, over, okay? So I have 55 miles over 1 hour. I want to be in kilometers per hour. So I'm not going to futz with this bottom number at all. I'm only going to mess with the one up top. And I want to go from miles to kilometers. Well, I think we kind of figured that out already. In our previous page, we wrote down a conversion that would help. Correct. So we have, for 1 mile, 1,600 meters. I'm going to go the long way. Now what do I need to do? My miles cancel, but I want kilometers. For every 1,000 meters, I have 1 kilometer. Okay, so I'm going to have 2 Sig Figs in my final answer. 55 times 1,600 divided by 1,000. 88. What are my units? Kilometers per hour. And to make sure, my meters canceled, and I only am left with kilometers and hours. Next up, a Japanese car is advertised as having a gas mileage of 15 kilometers per liter. 15 kilometers over 1 liter. Convert this to miles per gallon. Ideas. Okay, let's stop. We want to start with the top? Okay, so let's get kilometers to 1.6 kilometers in 1 mile. I'm good with that. Okay, now what do we do? Using what you have on the previous page. Quarts to gallon, yeah. So how many liters, how many quarts and liters? So I've got 1 liter, and I'm putting that on top so it cancels, is equivalent to 1.06, 1.06 quarts. Okay, now we can go back to our original system, and we have what? 4 quarts for every 1 gallon. Does that give me what I need? All right, so how many Sig Figs am I going to round to? 2 Sigs, and what do we get? 35. 35, what are my units? We got gallons on the bottom, miles on top. Miles per gallon. Next problem, we've got 2 more to do. For the next problem, it says the latest model of Corvette has a displacement of 6.20 liters. What is this in cubic inches? So now we're getting to those cubic ones. I don't know if you remember those that you did in pre-AP, but we have 6.2 liters. Any suggestions? There's a unit conversion that you learned in Chem 1. If I have a little box that's 1 centimeter on each side, teeny, it'll hold 1 mil. Okay, that's one that I want you all to, I don't ask you to commit a ton to memory, but this is a really important one. Okay? All right, so if I know that, I need to somehow get to milliliters here. So what's my conversion? So for 1 liter, I have 1,000 mils. Now what do I do? For every 1 mil, I have 1 centimeter cubed. Okay, let's keep going, and then we'll talk about what we have to cube. What's my relationship between centimeters and inches? The basic relationship. This is the simple one. Good. 2.54 centimeters to every 1 inch. Okay, so I can't cancel out centimeters and centimeters cubed. So what do I have to do? Now cube this and this. So whoever asked me, do I need to cube the mils? Do you see why you don't? 1 mil is 1 cubic centimeter. But in order to cancel those centimeters, I need to cube this relationship. What I cube up on top, I have to cube on bottom. What I cube, when I cube the unit, I also cube the number. You're not in pre-AP anymore. You're big boys and girls, so I'm not going to make you do 2.54 cubed and write it down separately. You can do it all on your calculator. So let's go ahead and give that a shot, and we're going to round it to our original 3 significant digits. That cubic inches, so I have an inch with a cube on top. Got it? Okay, last problem. This is awesome. This is an awesome problem. It says the density of concentrated sulfuric acid is 1.84 grams per 1 mil. So that's kind of equal to 1 mil, right? Concentrated sulfuric acid is 95% pure. What volume of concentrated acid contains 100 grams of pure sulfuric acid? So we need 100 grams of pure. Does anybody remember the formula for sulfuric acid? Nice. Good job. Okay. So this is the density of sulfuric acid. Is this pure sulfuric acid? No. 1.84 grams is equal to 1 mil. How much of this is actually sulfuric acid? 95% of it. So how many grams are actually in 1 mil? What do I do? 95% of. What does of mean? Times, right? So 0.95 of 1.84 is the amount I actually have in 1 mil. Does that make sense? So how much do I have? Stick with the 3. The percent's usually 2 decimals. So what is it? 1.75. So that's how many grams I actually have if it were pure sulfuric acid. So now it's just a dimensional analysis problem, folks. And it should be mil here, not liter, in 1 mil. So now the question's saying, how many mils would I need if I want 100 grams of pure sulfuric acid? So the question, what I'll have to figure out, and there's a couple ways you can do this. You can do it with dimensional analysis. I'm going to start out for every, and I'm going to flip this because remember, these are equivalent. And now it's actually 1.75 grams is equal to 1 mil. So in pure sulfuric acid, how many grams are in 1 mil? 1.75 of them. Is everybody okay with what I just did? These are equivalent numbers in the world of dimensional analysis. So how now would I figure out how many mils are in 100 grams? Multiply by 100. What did that do? Cancels a gram, so I get just mils here. And what is it? 57.1 mils. So I would need 57.1 mils of my original sulfuric acid to actually give me 100 grams of sulfuric acid. And that is all. Homework due tomorrow. 1A1. Wait, this is a new numbering system for me. I forget. Homework 1A. 1 is the unit, A is the first homework.